I'm going to go through one more example of calculating a volume of revolution that's calculated with the washer method. In this example, we have two curves. The first one is y over x squared is equal to 1. The second curve is y is equal to x. It's easiest to see what we're graphing if we isolate for y in both. So we have y equals x squared for the first one by cross multiplication, and y equals x in the second one. We'll eventually make a sketch. To help us with the sketch, let's find where these two curves cross. So when is it true that x is equal to x squared? So we have x squared minus x equals 0, and that common factor x times x minus 1 is equal to 0. We get two solutions. X is equal to 0 and x is equal to 1. And you can do that by inspection right at the very beginning. It says x squared is equal to x. You get the two solutions there. Next, let's make a sketch. Okay, there's our y-axis. X-axis. Next, we'll draw in the curves. Y equals x squared. So we'll draw that one in. That's y equals x squared. And y equals x. We'll draw that different color. Okay, so that's our graph. You can tell from the sketch that the green curve is further away from the axis of rotation than the purple curve. If you're not certain which is closer to the axis of rotation, it's definitely worthwhile to evaluate both functions at some intermediate x value. So if they're going from 0 to 1, if you plug in 1/2 into both, plug 1/2 into the first curve, into y equals x squared, you're going to get 1/4 as the y value. Plug 1/2 into the second curve, y is equal to x, you get 1/2 as your y value. So the higher y value is the green curve, y equals x. Consistent with the graph. Again, just like for area problems, making a sketch will either be mandatory or almost essential for solving the problem. Make a sketch either way. Okay, and then we're rotating this about the x-axis. Well, the x-axis, the line y is equal to 0. Another way of saying that. Let's see what that looks like in 3D. We'll do that in steps. So there's our line. It's going to be mirrored about the axis like so. And then we draw the purple part. Curve. Also mirrored about the axis. We'll shade in both parts. Okay, now it's shaded. And then we can imagine making it 3D. So this is like a bowl. Okay, that's pretty much what it looks like. Now when we slice it up, we're going to slice in the direction that gives us circular cross sections. Each cross section is going to be a cylinder. Okay, and then if we turn that on its side, so that's looking at it sideways as a thickness delta x, turn it on its side. Here's what the washer looks like. I'll label the axes. I guess I should use a different color. Okay, the distance from the center to the inner circle, we'll call that little r. And the distance from the center to the outer circle, big circle, I'll call that capital R. And I'll label it also on the graph on the left hand side. So that's your capital R up there. And then here's your little r here. Little r is always the curve that's closest to the axis of rotation. If you want to get the volume of the shape, or the surface area of this shape, the area is going to be pi times big R squared minus little r squared. The area of the big circle minus the area of the little circle. Our volume expression, volume, is the integral from a to b, from the left end point to the right end point, so from 0 to 1, of our area function, dx, integrating the x direction. Dx is our thickness, which we get by making delta x go to 0, turns into dx. Our sum over all these slices turns into an integral, and we'll sub in what our area function is. Integral from 0 to 1 of pi times r squared minus little r squared. So let's go back to our diagram. Little r is the distance from the axis of rotation to the purple curve. The purple curve comes from y equals x squared. So the y value, the height we get from x squared. And then for capital R, it's the green curve. We have the line y equals x. So the outer radius is x. So we can sub those in. We're going to get x squared. So our capital R was x squared, and the little r was x squared. We have to square that. There, that's better. So I'll label that. This part was r squared, and this part here was little r squared. Okay, now we'll simplify out the integral. Bring the pi out front, it's constant. We're going to go from 0 to 1 of x squared minus x to the 4 dx. Now it's a problem from chapter 5. Okay, take the antiderivative, evaluate on the bounds. Antiderivative of x squared is 1/3 x cubed. Antiderivative of x to the 4 is 1/5 x to the 5. And evaluating from 0 to 1. Going to get pi. When we evaluate both pieces at either piece at 0, we're going to get 0. So just going to be the first piece. So I evaluate at 1. 1/3 of 1 cubed is 1/3, and then 1/3, and then 1/5 times 1 to the 5 is 1/5. Multiplying each of those by 1. So I'm just going to hide that multiplication by 1. Now we need to do the common denominators to subtract the fractions. We have 5 minus 3/15. So our volume is going to be 2 pi divided by 15. And if you wanted to do a check, if this volume makes sense, you could look at a cylinder, a cylinder that contains that volume. So we're integrating from 0 to 1, and that cylinder that would contain it would go back to our picture. The y value here, what's the y value here? It's going to be 1 as well, where they touch. So this would be a cylinder. If you want to contain the whole shape, that would have a radius of 1 and a length of 1. Volume of the cylinder is pi r squared h. So we're going to get pi. And our answer has to be smaller than that. And our answer is smaller than that. 2 pi over 15 is smaller than pi. So our answer is sensible. If we got a number that was larger than pi, we have to go back and find our error. And that's one way you can check to see if your answer makes some sense.